Okay, welcome back to our machine design series. We are continuing our discussion of helical compression springs today by talking about fatigue failure. Now, we've talked about some static failure modes like buckling and closure, but today we're going to talk about fatigue because springs are almost always subject to fatigue loading. They're subject to high cycles very often. If you think about the valve spring of an engine, it's going to be constantly cycling many, maybe thousands of RPMs. And so we need to design those springs for an infinite life in fatigue. There is a surface treatment called shot peening, which is used to improve fatigue strength. So it involves bombarding the surface with a small spherical media. Small spherical media, which could be glass beads, metal beads, silica, usually, yes, steel, glass, or ceramic, at a high velocity. And what this does is it helps relieve any tensile residual stresses that exist on the surface and also induces some compressive residual stresses which are helpful to the spring in service. Now, the best data that we have for endurance limits, for torsional endurance limits of spring steels were published by a guy named Zimmerli in 1957. And what Zimmerli did is he discovered that no matter the size, material, or tensile strength of the spring, there was no effect of those variables on the endurance limit for wire diameters that are less than 3/8 of an inch. So the Zimmerli data give us alternating and mean shear strengths for peened and unpeened springs. So for unpeened springs, we have a shear alternating strength of 35 KSI or 241 megapascals, and a shear mean stress of 55 KSI or 379 megapascals. Squeeze that in there. Okay, and then for peened springs, so springs that have undergone this surface treatment where they've been bombarded with some kind of spherical media at a high velocity, those have a shear alternating strength of 57.5 KSI or 398 megapascals, and a mean shear strength of 77.5 KSI or 534 megapascals. Okay, and these data will be on your equation sheet if you're in my class taking an exam. And from these fluctuating stress values, we can estimate an equivalent completely reversed stress So remember, we've done something like this previously in our chapter on fatigue, where we used the Goodman criteria. So we're going to do that again. Use Goodman. But you could just as easily use any of the other fatigue criteria. And we find a estimate for this equivalent completely reversed stress, or as our endurance limit for this material. So it is our shear alternating strength, or stress, I suppose, divided by 1 minus our shear mean stress over our shear ultimate stress. So we have both the shear alternating and mean stresses from the Zimmerli data. So the only thing that these two variables depend on is whether or not the spring has undergone the shot peening surface treatment. And then the last piece that we need is this shear ultimate strength, which is also called the torsional modulus of rupture. And if we know the ultimate tensile strength, then we can estimate this as approximately 67% of the ultimate tensile strength. And remember that this ultimate tensile strength is a function of the wire diameter. We found an equation for that in the previous video. I'll just scroll up in the notes to highlight it for you, is this equation here. So you'll need to know your material so that you can find your constants A and M in table 10-4, and your wire diameter, so you can plug that in. Then this equation will give you ultimate tensile strength, and then you can go down and estimate your torsional modulus of rupture as 67% of that number that you get. Now, with an endurance strength and an ultimate strength, we can come up with a factor of safety for infinite life using the Goodman criteria. So the factor of safety for infinite life can be found using Goodman criteria. And we're going to adapt it for the pure shear case so that 1 over factor of safety in fatigue, that's what that subscript means for infinite life, is equal to our alternating shear stress divided by our shear endurance limit plus our mean shear stress divided by our shear ultimate strength, or torsional modulus of rupture. And just as a reminder, this is very similar to the Goodman criteria as we've seen it before, except in that case we were looking at normal stresses. So we wrote our equation as our alternating stress divided by the endurance limit plus our mean stress divided by the ultimate tensile strength. So directly correlated these two equations. The one that we're using for springs is just adapted for shear stress because that is the dominant stress in our spring wire, as we covered in a previous video. To find the alternating and mean shear stresses, we can use equations that we came up with in those previous videos. So the shear stresses, alternating and mean are. We use the equation with the Bergstrasser factor. So I'm just plugging in an alternating force instead of a static force into this equation, and everything else stays exactly the same. To find the mean stress, we do exactly the same thing, except we replace it with a mean force. Okay, so this is exactly the same equations that we've seen before. And our alternating and mean forces can be calculated if you're given just a maximum and a minimum force. You can calculate your alternating force as F max minus F min divided by 2, and your mean force is F max plus F min divided by 2. Now, a note for compression springs. When we talk about compression springs, these should never be subjected to tensile loads. They are designed to take compressive loads only. And so our F min should always be greater than or equal to 0. If F min is 0, that means that you have no preload. So our minimum force is a completely unloaded spring. And if F min is some positive number, then that means that we have a preload in the spring. And so even when it's completely unloaded, there is still a little bit of a compressive force. I shouldn't say unloaded. Even when, I guess in its minimum force condition, it still has some compressive load on it. And this is true for your ballpoint pen, for example. When you place the spring inside of your pen and you screw the tip back on, you'll notice that the spring gets compressed just a little bit. So even in its compressed condition or unpressed condition, you still have some compressive load that's on that spring. Okay, so that covers it for the fatigue of springs. It is very similar to fatigue analyses that we've done in previous lectures. So if you need to go review some of the stuff that we covered in chapter 6, then I would encourage you to do that because we're still going to use it. And other than that, the only new thing you need to keep in mind is this Zimmerli data, which helps us find the endurance limit for springs. And then we have this equation for the torsional modulus of rupture to estimate it from our ultimate tensile strength. Other than that, the rest of this is a repeat of information that we have covered in previous lectures. So this should be easy peasy for you. All right, so I hope this was helpful, and I thank you for watching this video, and I will see you in the next one.